Hello everyone, welcome back to another Stat 385 lecture. So in this lecture, I'm pretty excited for this one because I'm going to follow David Dalpiez's Moneyball in R script, and this will cover a lot about the tidyverse and about baseball analytics, and I'll just have a preview and a shout out for my course, Stat 430 Baseball Analytics. If this is something that you're interested in, then maybe you'll want to go through this and then consider my course, which will also be very dplyr and tidyverse heavy. Okay, so that being said, and I still want to say that yes, I am interested in baseball mainly from the analytics perspective, not necessarily from the game perspective. I guess you could say that I am a fan of the Cardinals, but I just don't follow it that closely anymore. I follow what's going on in the analytics space and how people are, or the approaches that they're using to assess the value of players, and that's my primary interest. And I'm interested in comparing players across eras. I'll get into some of that stuff a little bit later. Okay, so a little bit of sort of history about not necessarily Moneyball, but about like David Dalpiez and myself, our interest in it. So first of all, backing up a bit. So full credit to David Dalpiez for the materials in this lecture. David and I are collaborators on baseball analytics. We have a joint internship position with the Chicago Cubs where we worked with people there. We advise students. We work on baseball-related projects. We even work on Stat 385. A little bit of history of the course. Professor Chris Kinson and I created the current version of the course, and then I taught it a few times. And then after that, David Dalpiez's wife taught it. Then he taught it, and they've revamped it. And so now we've gone back and forth on what materials to include, and we've gone back and forth on baseball research. So this very much is very fun for me to see what he's done and to follow along on his write-up here and demonstrating the tidyverse. Okay, so now on to Moneyball. So I'm not going to get too deep into baseball. However, I think that this is a really good example of the power of statistics. So baseball has always been a game dominated by numbers to describe, or statistics to describe the value of players. And then, back in the day, they used relatively simple descriptive statistics. Means, for example, the mean, you can think of it as empirical success probability, batting average, hits divided by at bats. So it's just one thing divided by another. You could think of it as an average of Bernoulli outcomes if you like. And then that would be just the way at assessing who was good or not. Now we have all kinds of data that is collected and ways of assessing player values. But that all came ahead. This is something that I've been developing for a long time, studying statistics as a way to assess the value of players. But it really got going in the early 2000s with a baseball team called the Oakland Athletics, who was essentially looking for a way to compete with the clubs that spent a lot of money. And it turned out that there was there's many different ways of assessing player values, and they wanted to, in a sense, find metrics that translated better to on-field success than the more rudimentary metrics that were being used. And they were able to do this for a while and field really competitive teams, or rather, I should say, not because of the metrics, but they were used to, they had a competitive team, and they were able to use these metrics to sort of round out their roster and compete with clubs that spent a lot of money. And then the other teams caught on very quickly, and now everybody's using some sort of analytical approach to assess the value of players. And so now it's one of the things where you sort of have to be in this Moneyball space to just keep up. Okay, so again, kind of to summarize here, baseball has always been around, always been a game of numbers to some extent, and then statisticians or statistics inclined or analytically inclined people showed that there are better approaches for assessing the value of players as far as, which metrics to use, which translate to or predict on-field success better or describe on-field success better than rudimentary techniques. And so statisticians, data scientists, data analyst type people have now work in the space of baseball because they've been able to show value. So that could be anybody that could be any one of you. And that it doesn't necessarily mean that you've had to play baseball or like baseball. But it's a great example about the value of statistics, we'll say. Okay, so here is David's script. We're just going to go through this and create some of these graphics for describing baseball players, I guess. Yeah, so he wrote this in early March, and so he's saying, welcome to opening day. The baseball season has started. Baseball season is now over. We're in the postseason. So I guess that's kind of interesting. So, okay, so so what are we going to do? Oh, there's a nice YouTube link here to a clip from the movie Moneyball. I should say Moneyball was a pretty famous book written by Michael Lewis about the Oakland A's and how they're able to field the team analytically. And then there's a movie with Brad Pitt and Jonah Hill. And I can't just clip on this page here. The page is linked on the website, but I can't show it because I'm on YouTube and there's all kinds of copyright stuff. But it is here. See, there is the thing that is here. Okay, so let's see here. We are going to look at the all-time home run leaders. So for those of you who aren't familiar with baseball, a home run is, okay, so there's a person who throws a ball, there's a person who swings a stick, and if they hit the ball and it goes over the fence, that creates an automatic run. It's the best offensive event that you can do in baseball. It's the most valuable outcome. So we will look at the people who have hit the most home runs all time. Okay. And another reason why I like baseball data or baseball analytics is because there is just a wide variety of meaningful, interesting data that is just right at our fingertips. And just to demonstrate here. So I have a script that I'm going to call lawman.r, and that is an R package. There's an R package called lawman, which I'm going to load in with these other ones. And it basically contains a whole bunch of data frames containing just a bunch of information on baseball players. Okay, so in particular, we are going to use a few of them. And I'm just going to change them to Tibbles just for printing purposes. Okay, so batting. So let's view it. So this contains a bunch of information. So it contains, each row is a player indexed by an ID, year, and team. So it's not player-year combos because players can get traded or whatnot. And it contains basic offensive events for batters. So we can see HR, which is short for home run. Okay, so we could just select player, ID, year, ID, team ID, and home run, and you can see some information. Notice that we have data going all the way back to 1871. So baseball's been played for quite some time. So that's nice. Okay, so we're also going to need people. Tibble people. Okay, so what does this do? What's in here? So this is a bunch of descriptive information on the players themselves. So note that in the batters data set, there's no really descriptive information of the players. It's just all indexed by these player ID codes. So it's rather, I would say it's kind of annoying. But we can get the information on the people themselves by looking at the people data set. So this is going to have information on batters and pitchers, but you'll note that it has the same player ID unique identifier. So possible that we'll see some joins here. And then, maybe we want to also look at the Hall of Fame or data on the Hall of Fame. So we'll create the same data set that Dalpy has created, where we look by career home runs, and we'll see whether or not the people are in the Hall of Fame, noting that there's some NA values. Okay, and we'll get into some of that. So you would think that, Hall of Fame is essentially the highest honor that a player can receive, and you would think that people who were very, very hit a lot of home runs, who the most valuable offensive events, would be in the Hall of Fame. However, that's not the case, and we'll get into some of that. Okay, so let's display it, see what it looks like. Okay, that's annoying. Oh, that's better. So we can see player ID, whether or not they're in, or whether or not they were inducted in that particular year. Okay, great. So we want to create this table. So player ID, name, home run, in Hall. Okay, so we want to get seasonal, we want to take, so this batting data set is displaying home run per year per team ID. Okay, so that's not useful for us right now. Okay, so how about we could take one of these players. I don't like those players because there's an 1871 and I don't know who they are. So let's just arrange desk year ID. Let's look at these players. And let's look at this guy. This player is really good. I know I'm on Baseball Reference or Laman often, so I can read these codes. This player is a player who is very good this year, so we'll look at them. Okay, so how about I filter my player ID equals this player. Okay, so you can see that they haven't played for a lot of seasons, but in 2019 they hit his most home runs, 41, which is a pretty good score, or a pretty good amount of home runs in the season. Okay, so this looks like, so what I would want to do is essentially to get career home runs, I want to summarize home runs equals sum home runs. Okay, so this person through the 2022 data has hit 120 home runs. Now, I know that the 2023, for those of you who are baseball fans, I know that the 2023 season has ended. However, the Llama data set that I have is only through 2022. And I've checked it recently, and they haven't updated it. I haven't checked it that recently, so maybe they have updated it. But I'm going to just continue working through the 2022 data set. Okay, so this works. So again, I'm just kind of going through dplyr stuff right now. This right now works very well for one particular player. However, that's not very useful for me. What I want is to do this for all the players. And I'm going to go down a bit here because I want to stay relatively organized. Okay, so let's get rid of this. I don't need that arranged there. I don't need that. Okay, summarize home runs. Okay, so I just recently learned a trick where I can put the by inside of the summarize code, and I can just do player ID. Okay, what does this do? Cool. Okay, and then I can arrange by home runs. Okay, great. So now I see. Okay, so it's arranged by home runs. Okay, nice. Okay, so this isn't very useful because it has these goofy codes. And unless you have like a lot of experience with these codes, it's not really something that is very useful. And if you have no experience with them, they don't say anything. So let's look at this people data set. Okay. Let's do, I know I could just use the tibble directly, but okay. So here we see name first, name last, name given. Okay, so that's useful. So let's do people, select player ID, name first, name given. Okay, so name first, name last. So it looks like name given is first name, middle name. So that's not that useful. So maybe we just want name last. Okay. So that's nice. Let's take this thing and now join in people by player ID. Okay, so I can do this in a number of ways. Okay, so people contains a bunch of stuff I don't want, right? A bunch of columns I don't want. We have all this information. Like, I don't really care about a different ID or which country they died in or something like that. I want to create this table, player ID, name, home runs, in Hall. So I just need information on name. So I could do subsetting here, which is kind of, an interesting concept, or I could do the subsetting after I do the join. I'm just going to do that. Okay, so left join, and then I want to select player ID, name first, name last, home runs. Cool. Okay. And then I also want to use some tidier to unite those columns and just call it name. Unite name, name first, name last. And use a slight separation here, space. Even better. Great. Okay, so now we have descriptive information or we have names for these players. If you're baseball fans, this is gonna look pretty familiar, I would say. Okay, so now this last thing, this Hall of Fame data, let's look at it. Hall of Fame has two more variables, category, inducted. Okay, you know what? I'm going to browse it by, I'm gonna just, oops, sorry, what am I doing? I'm gonna pick a person who I know spent a long time in it. Ooh. I don't know how to spell this person's name. Eek. Oof. There we go. Okay, so you can see here, this player had, in 1998, was eligible, did not get inducted. In 1999, did not get inducted, so forth and so on, until 2011 got inducted. So we have a lot of information on particular players here. And I just want to know, did they get inducted? Okay, so what I need to do, I could do something like summarize, create a variable name in Hall, equals any inducted, and the code for that is Y, and I want to do this by equals player ID. Okay, so you can see the people who were inducted here. Well, it's true false variable, but it's going to have the information for all the people who have entered the process, who have received votes, I guess. Okay, so I can take that thing and I can see it has the same player ID. So this is what's really nice about all this baseball data, is that it's all given to you, and it's really good for demonstration purposes, especially this Lawman package, because all of these data sets I'm referencing use the same column player ID. It's in the same format, and so I can just join these things all together. So it's really nice, and you can see how this is something that you would have to do in real life if you were a data scientist. You'd have to be just joining together data sets all the time. So this is great practice for something that I like, and I hope that you like as well, or at least can see the appreciation for it. Okay, so I want to do left join. I want to create this tibble that I just created. You know what? I'm just going to take the code. Okay, summarize. Oh wait, but I actually need a Hall of Fame here. Why so? So I'm going to join a tibble by player ID. Oh, that's another thing. So this is the tibble that I want to join by player ID. Oh. Do I have to put that in quotes? I might. Oh yeah, in quotes. Okay. All right, great. Okay, so this is the variable. Nice. Okay, so it's a little bit different than David Dalpiez's. Why is it different? Oh, I think this must be through, okay, so this is through 2021, and Alex Rodriguez, maybe he wasn't yet on the ballot? Yeah, he might not have been on the ballot yet, and so he had no information in the data set. Pujols. So the way that it works is that it's 5 years after a player retires, and then they're eligible for voting. So this person here, who's hit a lot of home runs, hasn't appeared on the ballot because they retired really recently. Okay, so we can see here that there's a lot of people who aren't in the Hall of Fame despite hitting a lot of home runs. Why is that so? Because performance enhancing drug allegations, or they just did it. So it's been a whole thing in baseball and maybe sports in general about people who have been using banned performance enhancing drugs, or performance enhancing drugs that have since been banned, to essentially improve their performance. And it's been a whole debate. Long story short, those people are looked down upon by the baseball writers. There's a lot of opinions on that kind of thing. I don't know. I'm not going to linger on it too much. I think some of these players should probably be in the Hall of Fame because they were really good, and they were really good when they weren't thought to be on performance-enhancing drugs. Anyways, so this is what we're asked to do, this is what I wanted to do to demonstrate tidyverse and tidier, and we did it. Great, looks great. So notice that on his website here, he has this data table command. And then that's in this DT package, and that's creating inside of this this nice like web page that you see, this idea that this like sorting type stuff. Okay, so you can see. Actually, let's go down a little. Okay, so this person just made the Hall of Fame. Whatever. Okay, so that's that. Okay, so what's the next thing to do? Okay, so this is actually pretty interesting. So this is called Pythagorean theorem of baseball, and what this is just a extraordinarily simple equation that basically what's the way to describe it? If you have the number of runs that a team scored, two numbers, number of runs a team scored, and the number of runs allowed a team scored, then this equation should very accurately predict the team's winning percentage. And it's a very simple equation. It's this run squared divided by run squared plus runs allowed squared. And you can see some simple things in it, that if runs is greater than runs allowed, then this number is going to be greater than 0.5. Think about it for just a sec. Okay, there's also some pretty interesting things that happen with this. So, you sort of know that the more runs you scored relative to runs allowed, the better you are. But if you look at raw run differential and you say a team that scores 10 runs per game, I know this is totals, a team that scores 10 runs a game and allows 5 is the same as a team that scores 6 runs but allows only 1. On run differential, they're the same. On this equation, they're dramatically different, and just due to the nonlinear nature of this equation. And if you plug it in, you can see that the team that scores 6 on average and only gives up 1 on average is predicted to have a much better winning percentage. And if you think about it, that kind of makes sense. 10 versus 5, there could be a lot of a variability in both the 10 and the 5. But when you have 6 versus 1, maybe there's some variability in the 6, but in the 1, it's pretty constant. So it kind of makes sense that this just like generalizes beyond run differential. And it's great. What's also really cool about this equation is that it was discovered by a person with very little formal statistical training who, from what I gather, just stared at spreadsheets long enough to sort of intuit out this equation. And it is very, very solid work. And the person in question is Bill James, who's credited for sort of starting or popularizing the analytics movement in baseball. And so this person, not much statistical training, not much baseball training, full on outsider, and was able to sort of get the ground going on this analytics movement. And then it grew and grew and grew until, eventually the Oakland A's used Moneyball or analytics to start winning games. And then from there, once one team did it and was successful, now it's just the norm. Okay, so very cool background on this. I know David is looking at the movie, but the actual history is pretty cool. Cooler than the movie. Okay, so we're going to do this and investigate this equation. All right, so this is Pythagorean theorem of baseball. Winning percentage should be runs scored squared divided by runs scored squared plus runs allowed squared. Okay, technically a better equation can be given by an exponent that's slightly less than 2. If you take my baseball analytics class, we'll go into that. But anyways, okay, so let's investigate. Okay, so what do I want to do? Okay, so we don't need that anymore. Okay, we have our nice little table. We don't need this. Okay, so let's do, now we need information on teams. So we have League ID 1871, we have the teams, and we have total information on the teams. Well, total information. There's a lot of stuff that's in A, but that's okay. So here we have, again, total home runs, but the things that we're interested in are runs and is it earned run? No, runs allowed. There it is. Okay. And games. This is kind of interesting. This column here, they didn't play as many games as they do now, but I guess what's interesting to even the non-baseball fans watching this is that it's very variable. You think of baseball as like an institution that's very modern. And so when you go back to 1871, you can see like one team is playing 19 games and another team is playing 32. And then the next season, there is a team that doesn't even exist in the league and they played 50. So who knows what's going on. Okay. All right. So what we want to do, let's look at a more modern season, the most recent season. Okay. And let's select the things that are useful here. Year ID, team ID, wins. So we want to compare winning percentage to this equation and runs allowed. Okay. Yeah, that's what we want. So you can see this team was pretty good and their runs and runs allowed are dramatically different. Okay. All right, so then let's go on and create our variables. So let's do mutate. I want to create, how about win percentage equals runs squared divided by runs squared plus runs allowed squared. So we can see it. And let's do Pythagorean wins equals round 162 times this quantity we just created. So this is the estimate of wins based on the equation. Okay, well, that's pretty neat because the best team in this print display is predicted to have 102 wins by the very basic Bill James Pythagorean equation, and they won 101, so it's only off by 1. And here we have another really good team. It's off by 3. We have a really bad team. It's essentially the inverse of this one, and it's based on just the runs information. They were expected to win 63 games. So this is doing pretty well. Okay, so that's cool. So now let's ggplot. Let's like visualize this, see how it's doing. I can do the aesthetic right on the outside, which is to add. So let's look at the relationship between wins and predicted wins by our equation. Oh yeah, what am I doing? What happened? Oh. Switched to ggplot too soon. Okay, well that's annoying. That's really annoying. Wow. That's a pretty good line. Let's add a smooth. What's that smooth there? Almost a straight line. Very cool. Let's just make it a straight line. Use LM formula equals y total x. I believe it's just the default. So straight line fits it very well. Can I do, how's this work? Little quadratic. Did that do anything? Or do I have to actually specify this? Yeah, I have to specify it. So even though a linear fit may not, I mean, I don't know. I mean, we could test this fitting linear models, but even just like eyeballing a simple quadratic fit here doesn't actually improve too much on the linear fit. So essentially what this is saying is that actual wins and Pythagorean wins are pretty good. Look at the line, or look at the point 80, 80. It's basically right on the dot. So this very simple equation is doing a very good job. Okay, and also, I know we're not going to go into too much depth on these plots, but we can make it a little bit better. Okay, what team is this? Okay, so this team underperformed a bit, but they did really well. This must be that team we saw on the data set, the first 10 rows. Okay, great. Let's do the same thing and look at teams from, what's a good year? 1980. Oof. So what's going on? Actually, let's do 1990. It's not going to change too much. Okay, we got rid of some. It's fine. 1990. Okay, so it looks like there's a group here that would fit with a straight line really well, and then we have some pretty crazy seasons. So if you've been awake for the past few years, you may have heard about the COVID pandemic, and it affected baseball just like it affected everything else. There's a shortened season. So essentially what we're doing here, we didn't really pick the right scale of the variables to measure, because we're looking at wins as a total and this winning percent variable as a rate, and then we scaled it up to a total. And that doesn't work very well when there's major disruptions in the baseball season. So COVID being one of them, the season was shortened to 60 games. So here, team only won 30, or 30 less than 45, and they're predicted to win 150 based on this their runs and runs allowed, which makes sense if a team did really well by runs and runs allowed, and then you scale it up by, what did we scale up by? 162. So David actually is going to go through and fit these. Yeah, we should do it because it does demonstrate some coolness with mutate. Okay, so let's do it. Mutate. I'm going to create a variable season type. Oh, and I should say that's COVID. In 1994, there was a legit labor strike. So that messes things up. There's actually one in 95 as well. It doesn't look like, maybe that's that little group here, but it doesn't look like it has that big of an effect. Okay. Season time, and then there's this case when argument. Okay, so this is pretty cool. Year ID equals 2020. We can do COVID 2020 year ID. Default equals normal. Okay, so, and then I'm gonna color by season type. What did I do? Oh, geez, I'm being really silly. Okay, awesome. So we can get, so this is fitting, so this is essentially breaking this up and is fitting separate linear models for each of these different cases. And we can see that the straight line fit does pretty well for each one of them separately. And together, when we put it all together, we're getting something really silly because we have these extreme points here, which is just messing with the total line. But basically, we can see that the relationship between wins and predicted wins by our equation broken up across these different groupings of seasons does pretty well. Let's just add one more just to make sure. 1995, and we'll call it the labor strike continued into 1995, although it wasn't as dramatic. Yep, it was that group right there. Okay. Cool. Maybe there's some sort of Gaussian mixture model problem that somebody can do to classify the 95 seasons versus the normal. We're not going to do it here. Okay, cool. So that's nice. Now, instead of doing 162, we can just do games directly. So in COVID, there's 60 games. In 94, there's some number of less than 162 games. Same thing in 95. And then the normal is 162. And how does that look? Oh, I need to select it. Okay. And we basically get our straight line relationship back. Just to follow the David Dalpiaz script, we'll just get rid of 95. Actually, I like it better with 95. It looks like the lines are a little bit better. Very, 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 very cool. Okay. Nice. All right, so we have gone through, looked at home runs, this very simple equation here, and now we will do StatCast. Okay. So this is Baseball Savant, and what they do is they collect, actually, let's just look at one particular pitcher. Give a demonstration of this when it loads. Okay. So this is a player, a pitcher, person throwing the ball. And they have some basic statistics over here. But then they have all of this information on which pitches they throw, distribution of that pitch, at least by, what is this by? By velocity, miles per hour, how hard they throw it. And they have some where the league average is. So, and they have all kinds of cool visualizations. So this would be their fastball, where in the strike zone, or where they throw it, the location information by sort of a heat map here. So basically, to create all these plots, they have information on all of the balls that this pitcher threw. Moreover, they have all of the balls that every pitcher threw, dating back to 2015. However, the technology to track the data was fairly unreliable before 2017. So this is like a massive data set, right? All the balls thrown, and they have all this information on, location stuff, but they also have velocity, how much the ball spins, location, or arm location on where they released it in 3-dimensional space. This is in 2-dimensional space here. They have movement information, all kinds of stuff. And then they have a lot of stuff for the batters. If they swung, they have basic event stuff, but if they swung, how hard the batter hit the ball, how high in the air by angle, launch angle they hit it, and if I have my field, where sort of the angle that they hit it onto the field, all kinds of stuff. So it's a pretty big, it's millions of observations and a bunch of columns. So it's a pretty big data set. We're not going to do that part of it. I should say, okay, so let's save this. Great. StatCast, and there are some software packages for getting this StatCast data. These packages are developed by people in the baseball analytics space. Professor Jim Albert, which, give me 1 second here, is one of the authors of one of the canonical Analyzing Baseball Data with R books, which my Stat 430 baseball class will teach from that book. And I am proud to say that Professor Jim Albert has spoken in my class each time that it's been offered, and plans to do so again. So that's really cool for me and for everybody. And anyways, so people have developed using code that he has written, ability to scrape this StatCast data. And then David Delphi has taken that further and written his own package, which you can use to get that data itself. We're not going to do that, but this is what the code looks like. So basically, he has, where is BBD? Oh, okay. Oh, that's the code here. So he's created BBD package, short for baseball data, for actually scraping StatCast data. It's a nice package. I really like it. I teach it in my class. Okay, so basically, if you want to follow along and actually get the data, you should note that this will take a very, very long time to run, because essentially what it's doing is it's going to scrape all of the StatCast data from the 2022 season, and that is going to be millions of observations. Is it a million? It's going to be hundreds of thousands of observations, and it just takes a long time to do it. So be careful and note that. So he's already gone through the work of identifying where in this data set Dylan Cease is, the pitcher that we're going to study, what his advanced media, MLB advanced media ID is. That's going to be the key that StatCast uses. And then there's his key baseball reference. So he's gone through the work and found all the information on Dylan Cease, and he has compiled it into this Cease 2022 RDS file. Okay, so this is a different way of loading in data. Using an RDS file, we're going to use Cease 2022 as read RDS. Okay, so we covered reader in class. This is a sort of compression technique to make, I guess, the files easier to load, easier to save. Okay. What's going on? Oh. So I always like to organize. I got too excited about this lecture. I always like to say where I'm organized, how I've organized myself. I'm in the Stat 385 R project, as always. And I created a directory called Moneyball, and in it I have these scripts that I'm working on and editing, and I also have a data directory that contains this .rds file. So if you click here on Professor Dalpiaz's page, then it'll get this Cease 2022 RDS file, and you won't need to go through the work to getting it yourself. Okay. This is code that would create a strike zone. I'm not going to mess with it. I wonder, did he create this or did Jim Albert? I think it's a combination of either way. I think Professor Jim Albert he has an immense blog supporting this book with a whole bunch of just analysis scripts that he's now gone back and spent a great deal of time organizing. So I think David just pulled it from there. So anyways, this is going to create a strike zone for a visualization. Yeah, let's look at what we're trying to do. We're going to essentially try to recreate some of these StatCast graphics for Dylan Cease, this kind of stuff. Like where his pitches are going, and this plot right here. We're not going to recreate them perfectly, but we're going to approximate them. Okay. So we need information on all of the different pitches that he throws, and then we're going to look at the velocity distributions and then locations. Okay. Cool. So for this visualization, you can see here, this is the strike zone. So that's why that's created. Okay. So cool. We'll just run that. So what do we need to do? So we have Dylan Cease data. What does it look like? So we have pitch type that he threw, and we have release speed, release position. Okay, so we have the things that we need. There's a lot of stuff here. Okay, so first of all, let's just do some descriptive statistics. Let's look at how many times he threw each pitch. By equals C pitch type. We'll look at the StatCast encoding for the pitch and the pitch name. Okay, so he throws these pitches. Some of them he throws way more than others. Oh, he threw a slider quite a bit. That's cool. More than a fastball. Typically speaking, pitchers throw a straight on ball as hard as they can throw it. The four-seam fastball is what it's called. And that's usually the pitch that a pitcher would throw most often. So it's cool when you see somebody throw another pitch more than that one. A slider is like straight on, and then it sort of just breaks glove side. So if I'm right-handed, it'll break to the left a little bit. So that's fun. It typically doesn't have the same velocity as the fastball, and you trade off some of that velocity for some movement. So pitchers that can throw a fastball and a slider relatively from the same arm location or the same arm like position will do extraordinarily well. It will really fool the batter. And if you can mix in a bunch of other pitches that you have, good command of, then if you can release them from relatively the same location, you're going to be doing extraordinarily well. Okay, so we're not going to get into too much of that release point stuff, but yeah. Okay, so we can see here that there's also these NAs, and I think that that's because StatCast records event information for non-pitches too. Stuff like, I don't want to get just non-pitch information. We don't need to get into what baseball is at this level. Okay. So basically what we want to do is, that's cool. We want to remove the is.na stuff. Pitch type. Okay. ggplot. And let's create this first one where we look at the different velocity distributions. Okay, AES. The variable is called release speed. Okay, so that's on the x-axis. Oh, wait, what am I? Oh, no, I'm looking at something different first. Well, okay, sorry. Let's go back to what David did. Oh, yeah, we're doing this one first. We're plot release spin rate, release speed. Sorry. Spin rate. Well, okay, so let's look at this first. I keep doing this. geom point. Okay, so you can see here that there's some clusters, which is kind of cool. I don't know if you haven't seen baseball. This is actually a really good question for the people who haven't seen baseball before or don't know much about it. If there are 4 different pitches that this person throws predominantly, or it looks like 4 different clusters here. It looks like this gets a little bit skinny right there. So does it make sense to you that there would be some sort of give and take between speed and spin rate? So if I go back, cease 2022, and we do summarize n equals. Oh, I'm just gonna do pitch type. No, pitch name. It's more descriptive. Okay, so you can see that this person throws that pitch a lot, that pitch a lot, and that pitch a lot. You can kind of see him here. And then there's a few points just kind of scattered around. And there's another cluster here for something that's really slow. So probably this one, since I know baseball. It makes sense to me that these pitches would have different velocities. It wasn't intuitive to me necessarily that they'd have different spin rates. I mean, I know that now, but it wasn't at first intuitive. So anyways, interesting to see that. Actually, I don't even know now if they do. We have to color by pitch up. I do know because I've seen these types of graphics for now years. Okay. So we can see that changeup, knuckle curve, slider, fastball. So fastball typically has less spin. It's supposed to be a straight on ball, maybe with some backspin. And with a lot of velocity. Okay, so, and we can see, oh cool, we can see some sinkers in here because sinkers are like fastballs. They're typically, it's a little bit slower. Okay, cool. I'm just gonna say David doesn't like this color scheme. I think it's fine. But there is this argument or this layer here that allows you to change the color scheme. I guess it's nicer. And I'm gonna put this all in theme minimal. Okay, I know he likes black and white. He really likes the borders. I don't. Okay. And I think that a lot of people who do data visualization theory also don't like the borders. So maybe I should talk to David and tell him to see the light on this. Okay, great. So that basically creates this plot, which I think is a good one for getting started. Okay, so now we'll go and create the top one on StatCast. Okay, so we want cease 20. Okay, wait. Going too fast. We want to do this one. So we need to split by, okay. First of all, sinker is basically a fastball, and knuckle curve is basically a curve. We're not going to combine all of the pitches together, so it's not going to be the same graphic where he throws. You can see that there's 5 pitches here. There's only 4 here. Basically, this combines sinker with fastball. All right, so they're not going to be exactly the same. That's okay. So we want to first do this thing. Actually, we want to do all of this. Okay. And I want release speed again. Then I want y equals pitch name color equals pitch name. And then just a hint here. There's different packages that you've seen. GG Ridges has these different geomes, these different geometries in it for creating these nice little densities. So geome density ridge, no, ridges. Now I'm gonna just do the theme minimal now. Okay. Oops, what did I do? Don't like that. Fill. Yeah, looks pretty good. Okay, so not quite the same, but pretty good. You can see, yeah, you can see sinker and slider. That sinker is just a little bit slower. He throws a sinker pretty consistently despite not throwing many of them. One thing that's different here is it looks like this plot is actually doing distribution information relative to all of the other pitches. So this isn't fastball distribution necessarily. This is also, so this displays distributional information about the fastball, but also it includes the actual density that's depicted here is for like total fastballs among all pitches as well. And that's really apparent with changeup, which is basically just this flat line. Whereas this plot is like splitting them up and is doing density for each of the pitches separately. So even though this person didn't throw that many changeups, it's showing the wide or the density for changeups in particular, not relative to the other pitches. So that's a little bit of a notable difference. This density estimate is going to be very unreliable because, as we've seen, the person really only threw 76 changeups. Well, I shouldn't say it's guaranteed to be this unreliable because sinkers, he threw less sinkers than changeups, and that was actually pretty pointed. Okay, so maybe this person just doesn't have that good of command on a changeup. So work on it, Dylan. Work on your changeup. It's an important pitch. Okay, so oh my gosh, we are at an hour. This has been too much fun for me. Time has just flown by. Okay, so you know what? I'm just gonna copy this directly just to do it. Okay. Okay, David's using this pipe operator, the one in base R. Yeah, I've talked with him, and he says that they have improved it even since he taught his class. However, so okay, well, it doesn't matter. We'll just do it. Okay, so what's going on here? Okay, let's zoom in first of all. Okay, so we have the pitch types, we have locations in the strike zone, and we have sort of a heat map type of information on where the pitch was thrown in the strike zone. And of course we can see, oh, there's also some, what's it called? Transparency added to the point. So like when they are grouped close together, the region is darker. You can see the darker orange versus the lighter orange. It's really apparent when green and blue as well. Okay. All right, so what happened here? So he constructed the strike zone for right-handed hitters. Wait, what? Pitcher name, batter name, stand. Okay. So he's filtering by pitches thrown to right-handed hitters. Okay. So that's fine. That's just because a pitcher may have, I'm gonna just move. Okay, a pitcher may have a different throwing regimen against left-handed batters. Okay, so that's fine. Get rid of the NAs, GG plots. We're doing aesthetics on the XY location. It's given by Z in StatCast. The Z-axis instead of the Y-axis. Okay, so this Geom HDR is from this GG density. I think it's from GG. Let's see. Yeah, GG density. So that's doing the highest density region. And then he's plotting these different regions here. Okay, and so let's look at them. Let's look at the plot again. Is it already zoomed? Okay, so this light gray, this really, really light gray. So this entire region is essentially where 95% of this pitch sinkers are thrown. The really light gray for here is sliders, and the next lightest gray is 75%, and then here is like the 5% highest region. So he's essentially against right-handed hitters. He's basically trying to aim his slider down here. Okay, fastball right there. All right, so then he adds the strike zone, which is this thing, which is created here, to the visualization. And then he adds points for the pitches. This adds that transparency. We could change this. So now it gets really light. I kind of like that better. Or you could just remove it, which may not be a bad idea. So this would be more like what they did on StatCast, right? We have here, I mean, the regions range from red to blue, but here they're just ranging from light gray to black, no actual point information, and then a bunch of stuff to change the themes, change the color palette, and then at the end is this facet wrap to split the distributional information across the pitches, which is really nice. Okay, so this is a lot. If you're still here, which is great, I will say that, so David and I, going too far back, have a active collaboration going on baseball stuff. And I should say that we are not the only ones. There's also Alan Nathan, who is a professor of physics. And he has, Well, anyways, Alan Nathan is a pretty big deal in the space of baseball analytics, and he's a physics professor. He's been doing baseball type work from a physics perspective for a very long time. He just gave a very interesting talk on looking at bats that are, like the same wood from the same company, and finding variability in the composition of the wood. And can show he can basically pick up a bat and tell you if it's going to be better for a hitter or help you hit the ball further. So that was a really cool talk. And then so this is my work here. So this is a project where I take some baseball statistics, which are cool for summarizing career value of a player, a statistic called wins above replacement. And then I came up with a statistical mathematical model for that allows for an error adjustment for that statistic. And there's a whole bunch of material on what I did. This is I shouldn't say me. This is a collaboration with my graduate student Shen Yan and history professor Adrian Burgo. So it's a really interdisciplinary team here. And then also statistics professor Chris Kinson. And so here we have all these, and we don't just have this statistic, we also have a bunch of error-adjusted batting statistics for players. So this is the kind of thing where if you are interested in comparing players across eras or are into these debates or whatever, you can reference our webpage on this and get error-adjusted, like a more error-adjusted approach for this. So basically the argument is that back in the old days, a player like Babe Ruth stood miles above their peers just due to there not being many high-quality peers to populate the MLB. And when that happens, then amazing outlier in talents like Babe Ruth, he is an amazing outlier in talent, can just stand so far above the pack in a way that is unrealistic by today's standards. So our model tries to balance how far you stand from your peers when you play against the size of the actual eligible talent pool from the time period that you played in. And we can do that. Paper currently under review. And once it's under review, we have our new results. We are going to update this website. Broad strokes, these top few rankings aren't going to change too much once we do the updating. And we also have a different version of WAR, and you can see this. Okay, so I'm really happy with that project. And then also there's a project that David and I collaborated on for estimating batted ball distributions when a particular batter faces a particular pitcher. So here you can see, it takes a bit to load up front. So this is when this pitcher faces this batter, what the outcomes on the field are likely to be when a ball is hit into play. And if I switch the pitchers, it changes quite dramatically. Okay, so this is fun as well. Alan Nathan. Let's just look at these links as well. This is all stuff going on at University of Illinois. Some of it's my own stuff, but some of it is not me. It's very interesting. Okay, so this is a good article on the work that I did with Shen and Adrian. And this is on my baseball class. You can see here Charlie Young is mentioned. So Charlie Young is a student that David and I met. He mostly worked with David and Alan Nathan, but he did work with me as well on that SEAM project for batted ball distribution estimation. And he was, he's very not happy that this course wasn't offered in my baseball class when he was here, but there's some other students quoted who were in that class who now work in baseball as well. So there are a recent crop of Illini students who now work as analysts for baseball teams. We also have, as an alumni, the current assistant general manager for the Cubs, and me, and his name is Essen Bakari, and me, Essen, and David work together on an internship where students can get experience working with analytics, advised by David and myself, but Essen as well. And we try to work on projects that are useful for the team. Charlie Young created the Illini Analytics Club. They actually have worked in the past with the University of Illinois baseball team. He's done a lot of good work, and he is rising up at the Astros. So that's pretty fun to see. Okay, so a lot is actually going on here. I still maintain that I am in baseball for the analytics, not for the game, but it is fun to see all of the people who this university has produced within this space. Okay. Yeah, I don't think I have anything more to talk about. It's already been a very long video. Thank you for your attention, and I hope that this was very productive for going through and demonstrating the power of dplyr, tidyr, and ggplot. I mean, this is pretty cool the way it's able to merge or take all these data sets and put them all together and display all these different visualizations that are incredibly useful within the space of baseball analytics. But you can see how these concepts will generalize well beyond baseball. Okay, I'm still rambling. Thank you for watching. If you made it to the end, great job. Take care, and I will see you next time. All right, bye.